The Mathematics of Music, a lesson presented in MGF 1107, Explorations in Math. Now this is a course that's taken by non-STEM majors, so general liberal arts students. Our syllabus for the course states, this is a survey course covering topics which demonstrate the beauty and utility of mathematics to the general student population. Now, when they say the utility of mathematics, I prefer to think of that as the significance of mathematics. What we're trying to make you see in this course, or help you see, is how math surrounds us, how it's embedded into the world in which we live. It's woven into the fabric of life. So it's in the electricity that you use when you turn on the light switch. It's in the plane that you fly on. It's woven into the music that we listen to. When we listen to music, we may not be aware of the underlying mathematical structure of the music, but nonetheless, it's there. So in this course, we're going to learn to recognize and appreciate it. Our objectives in this lesson are, we are going to define the system of 88 notes used in Western music. We're going to explain the relationship between musical pitch and sound wave frequency. We're going to apply geometric sequences to find the frequencies of musical notes. And we're going to identify musical intervals, or in other words, pitch relationships. A piano keyboard has 88 keys, each corresponding to a distinct musical note. These are the notes used in Western music. As you can see, some of the keys are white and some are black. The keys are arranged from left to right in order of ascending pitch. The note with the lowest pitch is the far left key. The note with the highest pitch is the far right key. The notes corresponding to the white keys are named with the capital letters A through G. So we see here A, B, C, D, E, F, G, A, B, C, D, E, F, G, and then so on over and over all the way up the keyboard. To name a note corresponding to a black key, we add a sharp symbol, which looks like this, to the letter name of the white key directly below it, or we add a flat symbol, which looks like this, to the letter name of the white key directly above it. So for example, the note between C and D can be named either C sharp or D flat. So for instance, here is a C, here's the D right above it, and then in between we have the black key, and so that note that I'm playing here can be either C sharp or D flat. It's the same note, but we can give it either of two names. Many notes share the same name and therefore belong to the same family of notes. So for example, the C notes, we see them mapped out here. I can play them for you. So we've got the following C notes. As you notice, these notes, they're distinct from one another, but nonetheless they sound very similar to each other. That's why we make them into a family. So all the notes within a family which share the same name sound similar. Now why do they sound similar? Each note seems to be a lower or higher version of the other notes in the family. So just going back to my C notes, I won't do all of them, but here's a few. You see, they all sound very similar. Why? Because all the notes in the family are one or more octaves apart from each other. Any two notes that are one or more octaves apart sound very similar to each other and hence belong to the same note family. So all the A notes are one or more octaves apart from each other. So for example, I won't play all of them, but here's a few. All the B notes are one or more octaves apart from each other. And so on. There are 12 note families. We have the family of A notes. We have the A sharp or B flat family, the B family, the C family, the C sharp or D flat family, the D family, the D sharp or E flat family, the E family, the F family, the F sharp or G flat family, the G family, and the G sharp or A flat family. So 12 different note families. Now, if we take the range of the keyboard between two consecutive notes with the same name, which are, in other words, from the same family, so for example, from C to C, we call that an octave span. And you'll see that an octave span encompasses a note from each of the 12 note families. So you see it on the screen there. Let me play it here. An octave span from one C to the next C. So we have C, C sharp or D flat, D, D sharp or E flat, E, F, F sharp or G flat, G, G sharp or A flat, A sharp or B flat, B, and then the next C. So you can do an octave span between any two notes that are one octave apart. It doesn't have to start at C, it can start anywhere. If we want to assign a unique designation to each note on the keyboard, we attach a numerical suffix to its letter name. Lower numbers indicate lower pitches, and higher numbers indicate higher pitches. So just talking about the white keys, we have the notes A0, B0, C1, D1, E1, F1, and so forth, up to the highest note on the keyboard, C8. So just to show you here, A0, B0, C1, D1, E1, F1, and then the final note at the top, the highest note on the keyboard, C8. So the notes in the C family each note can be uniquely identified as follows. We have C1 through C8. For the D family, we have D1 through D7. There is no D8 because the keyboard doesn't go up that high. We have the notes in the B family are B0 through B7, and so forth. Now, the pitch of a note is dictated by the frequency of the sound wave. The frequency of a sound wave is the number of cycles of a sound wave occurring per second. A cycle of a wave is a section of a wave from one crest to the next crest. So the number of cycles per second, that number is the frequency of the sound wave. Frequency is expressed in hertz, which means cycles per second. So if you have a sound wave where there are 500 cycles occurring per second, then its frequency would be 500 hertz. When two notes are an octave apart, their frequencies are in a 2-to-1 ratio. The frequency of the higher note is twice that of the lower note. The frequency of the lower note is half that of the higher note. So for example, the frequency of A1, that would be this note, is 55 hertz. The frequency of A2, which is this note, is 110 hertz. So we see there's a 2-to-1 ratio between these frequencies. 110 is twice 55, and conversely, 55 is half of 110. So the frequencies of the A notes from A1 through A7 are as follows. A1, 55 hertz, A2, 110 hertz, A3, 220 hertz, A4, 440 hertz, A5, 880 hertz, A6, 1,760 hertz, A7, 3,520 hertz. So those are the notes here. A1, A2, A3, A4, A5, A6, A7. But remember that there's a lower note. In fact, the lowest note on the keyboard is A0. So I left that out because I want to quiz you on that. Can we figure out the frequency of A0? Now, it's one octave below A1, which has a frequency of 55 hertz. They have a 2-to-1 ratio, so 55 is twice the frequency we're looking for, or in other words, the frequency we're looking for is 1/2 of 55. But that's not a whole number, is it? 1/2 of 55 is 27.5. So the frequency of A0 is 27.5 hertz. The frequencies of the A notes form a geometric sequence. So starting with A0 and going up to the top, we have 27.5, 55, 110, 220, 440, 880, 1,760, 3,520. Now, this should sound familiar because our previous module was on number theory. So we learned about geometric sequences there. So let's just review what we learned. In a geometric sequence, each term is the preceding term multiplied by a fixed value called the common ratio. So, for example, leaving music aside for a second, just doing a quick review of the kinds of things we were doing in the previous module on number theory. Suppose we have a geometric sequence where the first term is 4 and the common ratio is 3. So starting with 4, the next term would be 4 times 3, which is 12. The next term after that would be 12 times 3, which is 36. The next term after that would be 36 times 3, which is 108. And if you keep going, you'd have 324, and so forth. Now, in theory, a geometric sequence can go on forever. But in our case, we're going to have a finite sequence because there's a limited number of notes on the keyboard. So for each note family, the sequence of frequencies is geometric with a common ratio of 2. We already saw the sequence for the A family. That would be the same for each family. It would be geometric with that same ratio of 2. Now, C4 is a special note. It's called middle C. You might have heard of that, middle C. So that refers to C4, which is this note here. Now, here's a little quiz. If C1, the lowest C, has a frequency of 33 hertz, then what's the frequency of middle C? Well, we can see here that to go from C1 to C4, you go up 1 octave to get to C2, another octave to get to C3, and another octave to get to C4. So each time you go up an octave, you're doubling the frequency because of that 2-to-1 ratio. So if we double 33, we get 66 hertz. If we double 66 hertz, we get 132 hertz. That brings us up to C3. If we double that, we get 264 hertz. So that would be the frequency of C4. Tuning systems are systems for determining the pitch of each musical note in the system. There are 2 major systems that have been used historically. Others have been used as well, like Pythagorean tuning, but the 2 most important historically are just intonation and equal temperament. So those frequencies that I was just using a moment ago for C1 and C4, that's in just intonation. Equal temperament is the predominant system in the modern Western world. It was developed in the time of Johann Sebastian Bach and has now been in widespread use for over 2 centuries. In equal temperament, the 12 notes within each octave span are evenly spaced out in a proportional sense. What that means is the increment from one frequency to the next is a fixed percentage increase. But fixed percentage increase is the hallmark of the geometric sequence. That's what we learned in our module on number theory. So let's just review for a second. Suppose we have a geometric sequence where the common ratio is 1.03. That means that each term is 3% higher than the preceding term. Now we can go the other way around. If you tell me the percentage increase, I can then infer the common ratio. So for example, if you tell me that you want each term to be 12% higher than the preceding term, that dictates that the common ratio must be 1.12. In equal temperament, frequencies are based on a geometric sequence. Now, what is the common ratio? Now, if you were just doing the notes within one family, we already said that the common ratio is 2. But if you want a geometric sequence that gives you every note on the keyboard, encompassing all the families together, you need something more complicated. What you need is a common ratio, which is the 12th root of 2. You can write that in radical form, 12th root of 2, or you can write it in exponential form, 2 to the 1/12th power. Now this is an irrational number, which means that its true decimal representation would be an infinite non-repeating decimal. But if we round it, it's approximately 1.05946. So that means that the percentage increase is about 5.946%. In other words, when I go from any note on the keyboard to the next note, or if I go from, in each case, that is a 5.946% increase in the frequency. Now, let's see how the system works in a little more detail. Let k be the frequency of any given note. If we go up one note above that starting note, we multiply the frequency by 2 to the 1/12th power, so we get a frequency of k times 2 to the 1/12th. If we want to go up 2 notes above the starting note, we multiply this frequency by 2 to the 1/12th again. But now we're multiplying 2 powers with the same base. So what do we know we do there? We add the exponents. So 2 to the 1/12th times 2 to the 1/12th gives us 2 to the 2/12ths power. So we get a frequency of k times 2 to the 2/12ths. Now you could reduce the fraction 2/12ths, but it's better that we don't. I'm not going to reduce fractions because I want to maintain a consistent denominator of 12 throughout this discussion. It simplifies the analysis and works better that way. If I go up 3 notes above the starting note, I take this note and multiply it by 2 to the 1/12th. Now, I'm multiplying powers with the same base. I add the exponents. 2/12ths plus 1/12th gives us 3/12ths. So we get a frequency of k times 2 to the 3/12ths. And here you see how it keeps going. Up 4 notes, k times 2 to the 4/12th. Up 5 notes, k times 2 to the 5/12ths, and so on. Now, when you go up 12 notes above the starting note, you get a frequency of k times 2 to the 12/12ths. But 12/12ths is 1, and any number to the first power is itself. So 2 to the 12/12ths is 2 to the first power, which is just 2. Thus, we get a frequency of k times 2, or in other words, 2k. Aha! That is the frequency 1 octave above the starting frequency k. Remember, that's the 2 to 1 ratio. So this is why the system has been designed so that it's geometric with a common ratio of 2 to the 1/12th power. Because that way, whenever you go up 12 notes above any given starting note, you necessarily arrive at a note 1 octave above the starting note. Now let's generalize the pattern that we see here. Going up n notes above k, the frequency will be k times 2 to the n/12ths power. And you don't have to stop at 12. You can go up further, and the formula will still apply. So for example, if we ascend 53 notes above the starting note, then we will obtain a frequency which is k times 2 to the 53/12ths power. Now, let's say we want to generate the frequencies of all the notes on the keyboard. This is what would be called a chromatic scale, by the way. And so on, all the way up to the top note. So our starting note, A0, the lowest note on the keyboard, we've already discussed has a frequency of 27.5 hertz. If we go up 1 note, we'll be at the note A♯0. Okay, so hang on. Here's A0. Going up 1 note above that, we have A♯0. You could also call it B♯0. The frequency would be 27.5 times 2 to the 1/12th. That gives us approximately 29.14 hertz. Going up another note, which puts us 2 notes above the starting note, now we have the note B0. The frequency will be 27.5 times 2 to the 2/12ths. That gives us about 30.87 hertz. Going up 3 notes from the starting note, now we're at the note C1. The frequency would be 27.5 times 2 to the 3/12ths. That's about 32.70 hertz. Oh, and by the way, before I go further, let's just notice, earlier we talked about C1 having a frequency of 33 hertz. That was not in equal temperament. That was in just intonation. This system here, based on the geometric sequence, is the system used in the world today. And in this system, in equal temperament, you don't have 33 hertz. You have something that's off a little bit from that. You have 32.70 hertz. Now, we know that there are 88 keys on the keyboard, and the top note is C8. And since the bottom note is A0, C8 is 87 notes above A0. So if I want to calculate the frequency of C8, that's this note, then we take 27.5 times 2 to the 87/12ths, and that gives us 4,186.01 hertz. That's the frequency of our top note, C8. Middle C, now before we addressed it in the context of just intonation. But in the equal temperament system, middle C is 39 notes above A0. So its frequency would be 27.5 times 2 to the 39/12, which gives us 261.63 hertz rounded. So that's different from what we had before when we were talking about just intonation. The frequency of middle C was 264 hertz. So you see we're off a little bit here. Now, when you hear a sound occurring in nature, generally you are not hearing a pure tone. Rather, you are hearing a cluster of closely related tones. The most important of these is called the fundamental tone, and that would be the one which has the lowest frequency. Now, all the other tones in the cluster are called overtones. The frequency of each overtone is a whole number multiple of the fundamental frequency. The whole numbers being 1, 2, 3, 4, 5, 6, and so forth. So your overtones will have frequencies that are 2 times the fundamental, 3 times the fundamental, 4 times the fundamental, 5 times the fundamental, and so forth. A musical note with fundamental frequency x has the following overtones. The first overtone will have frequency 2x, 2 times x. The second overtone will have frequency 3x. The third overtone will have frequency 4x. The fourth overtone will have frequency 5x, and so on. The overtone series is the basis of musical harmony. Harmony is defined in terms of musical intervals. A musical interval is a relationship between two pitches. Now, we've already discussed the most important interval, which is the octave, which is based, as we've already discussed, on having pitches in a 2-to-1 ratio. So the higher frequency is 2 times the lower frequency. This comes from the ratio of the first overtone to the fundamental. So the fundamental frequency, let's say, is x. The frequency of the first overtone would be 2x. You take the ratio of 2x to x. The x's cancel out. You get 2-to-1. That's our 2-to-1 ratio. The next most important interval is the perfect fifth. Here, pitches are in a 3-to-2 ratio. Now, 3 divided by 2 is 1.5. So this means that the higher frequency is 1.5 times the lower frequency. Now, this also comes from the overtone series. Specifically, it comes from the ratio of the second overtone to the first overtone. So again, if the fundamental frequency is x, your first overtone is 2x, your second overtone is 3x. We take the ratio, 3x to 2x, the x's cancel, you get 3-to-2. That's your perfect fifth ratio. And then the third most important interval in music is the major third. Here, pitches are in a 5-to-4 ratio. Now, 5 divided by 4 equals 1.25. So that means the higher frequency is 1.25 times the lower frequency. Now, this comes again from the overtone series. It comes specifically from the ratio of the fourth overtone to the third overtone. So your fourth overtone has frequency 5x. Your third overtone has frequency 4x. The ratio of 5x to 4x, the x's cancel, you get 5-to-4. Now, let me demonstrate on the piano. So here's an example. Well, we've already seen examples of the octave, but let me just do a fresh example. An example of a perfect fifth would be as follows. And an example of a major third would be as follows. Now, let me just mention that musicians train themselves to have very sensitive hearing when it comes to being able to hear and identify musical intervals. This is called ear training. And some people just have a natural gift for it, but most people will have to work at it. So one of the tools that we use in developing an understanding of intervals and an ability to identify them is to use certain reference songs, which are famous songs that everyone knows, and give you prominent examples of intervals. So let me give you examples of these three intervals. So for the perfect octave, the classic example of that would be the song Somewhere Over the Rainbow from the great movie The Wizard of Oz. So, for example, if we do this, somewhere over the rainbow. So the first two notes, somewhere, that is the octave. Now, for the perfect fifth, the classic example of that would be the theme song from Star Wars. Da, 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 da. But the first two notes, da, da, that's your perfect fifth. And then for the major third, the classic example of that is When the Saints Come Marching In. Oh, when the saints, so oh, when, da, da, that's your major third. So let me give you a quiz. I'm going to play a few intervals and see if you can spot which interval I'm demonstrating, all right? So how about this one here? Can you see what that is? That's the perfect fifth. How about this one? That is the octave. Try this one. That's the octave again. How about this one? Perfect fifth. How about this one? Major third. How about this one? Major third again. How about this one? Aha! I played a trick. That's not any of the intervals that we talked about. Now, of course, there's plenty of intervals that we have not discussed. That particular one is a diminished fifth, also known as the devil's interval, the intervallus diabolique. So it sounds kind of off. They use that interval, by the way, in the theme song for The Simpsons, because you want kind of an off-kilter sound for that, because of the nature of the humor. So let's just do a quick review. In this lesson, we have defined the system of 88 notes used in Western music. We have explained the relationship between musical pitch and sound wave frequency. We have applied geometric sequences to find frequencies of notes, and we have identified musical intervals or pitch relationships. So once again, our goal here has been to help you see how mathematics undergirds the music that we listen to, just as it does almost all aspects of life. But here our focus has been on music. You don't have to be aware of this in order to listen to the music and enjoy it, but whether you're aware of it or not, the mathematics is there. So thank you very much.